Welcome, friends. Last lecture, we have seen the various aspects of underground cable, like its structure. Then we have seen the advantage and disadvantage of using underground cable. Thereafter, we have seen what is insulation resistance and how it is varied as a function of length of the underground cable, and lastly we have seen the electric stress variation and electric stress variation of underground cable, and lastly at the end of the lecture we have seen that if D is equal to E by R, that is known as optimum cable geometry. So till that point we have undergone the underground cable chapter. Now today we shall see some more new aspects of underground cable. So we will be going to see that. So today we shall first start with this topic. It's called capacitance grading. It's called capacitance grading. Now what is capacitance grading? Now from the previous day lecture, one interesting observation you must have noticed that it is the variation of electric stress is following the rectangular hyperbolic curve. This is conductor and this is dielectric surface. Okay, so maximum stress occurs on the conductor surface and minimum stress occurs on the dielectric surface. And now this capacitance grading typically useful to achieve uniform stress in different layer. However, now what do you mean by uniform stress? I am coming in a minute. Uniform stress, I am coming in a minute. However, it is good. You can do a nice expression on pen and paper. However, this is impractical. This is impractical, very hard. Practically, it is very hard to achieve uniform stress. Practically, it is very hard to achieve such cases, though such type of model really exists. Okay, in our switch gear and switch yard, this type of model or this type of capacitance grading model exists. Okay, so this is very important to analyze the capacitance grading model in reality. What is the behavior and what will be the electric stress, variation of electric stress in reality. Now what is the capacitance grading? Now capacitance grading is a model where you have a central conductor like this. You have a central conductor like this. So this is the core. The central conductor is the core. And surrounding to that we have 1, 2, 3. That means different dielectric mediums having different radius R1, R2, R3. So let us say this white region. White region is dielectric one having permittivity epsilon R1. Now the yellow region is the another medium having dielectric strength or the relative permittivity epsilon R2. And let us say this gray region is the third dielectric medium having dielectric permittivity epsilon R3. So in this way we have n number of layers surrounding to the core, and we are interested to find out what will be the stress on these interfaces. That means what will be the stress at this point, that means conductor surface. What will be the stress on the dielectric interface, various dielectric interfaces, and the variation of stresses. So this is our main interest. Now such models, as I told you, such models really exist in reality. I'll tell you the example, what type of the model, the practical example. So let us proceed with some mathematical derivation. Now before proceeding, we require this expression. Okay, we require this expression which was done previously, that is Ex, that will be is equal to, I'm writing again, Ex, that will be is equal to Q by pi epsilon 0 epsilon r, then we have 1 by x, right? We have 1 by x. So we require this expression. So I am writing that expression beforehand. We require in a moment. Now let us coming to this model. Now let us assume the outermost dielectric medium that is grounded. So the total potential difference is V. Total potential difference is V. Total potential difference is V. Now what is V? V I am assumed to be summation of three voltages, V1, V2 and V3. Summation of three voltages. Now what is V1? Now V1 is the voltage difference of this layer. This is V1. Actually I am using different color. So this is actually V1. That means the potential drop of the dielectric medium 1. Similarly, we have V2, that is the potential difference of dielectric medium 2. And lastly, we have potential difference V3, the potential difference of dielectric medium 3. So if we add these three, V1 plus V2 plus V3, we will get the total potential difference. Now what is V1? V1 is, I am writing the expression from the definition of the potential. V1 is minus integration Ex dx. Now this integration should be carried out from let us say this point to this point. Okay, so this point signifies it is R1. Okay, this point signifies R1 and this point signifies R. So that integration should be carried out from small r1 to R. Now similarly we have V2. V2 again, from the definition of potential, we will have Ex dx. Now this time integration should be carried out from R2 to R1. This is R2 and this is R1. Okay, so this is R2 to R1. Now similarly V3 is same thing, minus of Ex dx. Now this time integration should be carried out from R3 to R2. Okay, so integration should be carried out from R3 to R2. So this is the expression of V1, V2, V3 respectively. Okay, now what is Ex? So Ex, from this expression you can straight away write down this. Okay, so I am writing the first equation. Now I am removing this minus sign, so I am removing this minus sign, so the integration limit will be changed. So it will become smaller to smaller 1. Now Ex should be Q by 2 pi epsilon 0. Now Okay, now this time, now as you see, the integration is done from R to R1. That means from R to R1 in this medium. That means in this medium, right? So it essentially tells you this medium corresponding to epsilon R1. This medium corresponding to epsilon R1. Okay. So in place of epsilon R, you should write, or one should write epsilon R1 here. One should write epsilon R1. Okay. So I have written what is Ex. What is Ex? Ex is equal to Q by 2 pi epsilon 0 epsilon R1. Now dx by x. Now if we come to the second expression, this expression will become the same thing. The minus will become plus, so the integration limit will change. It will be R1 to R2. Now what is Ex? It will be Q by 2 pi epsilon 0. Now since the integration is done, from R1 to R2, from R1, integration is done from R1 to R2, right? So it is denoting this. Actually, it is denoting this this region. That means dielectric medium 2, which is characterized by a dielectric interface or the relative permittivity epsilon R2. This is epsilon R2. So one should write epsilon R2 in this place. Okay, epsilon R2. Then we have dx into dx by x. And finally, we have the third expression. Similarly, if we remove minus sign, so integration limit will change. It will become small r2 to small r3. The same expression, q by 2 pi epsilon 0. Now this time it should be epsilon r3 because it is denoting the third dielectric medium. So it will be dx by x. So from this expression, we can write V is equal to, therefore V is equal to, now if you observe closely, everywhere you see q by 2 pi epsilon 0. This is common. Q by 2 pi epsilon 0, this is common. Now in the first expression it will be 1 by epsilon r1 ln r1 by r, right? From the second expression it should be 1 by epsilon r2 ln r2 by r1. And lastly, from the third expression it should be 1 by epsilon r3 ln r3 by r2, ln r3 by r2, ln r3 by r. So we have this expression. Now if you look carefully, this expression inside this square bracket, this entire expression, the entire thing inside this square bracket is constant. Why? Because the dimensions are constants. You see r. So this entire thing is constant. Why? Because these dimensions are r1, r2, r3, all are constants. And more or less, moreover, epsilon r1, epsilon r2 and epsilon r3 also constant. So this entire expression becomes this entire thing inside the square bracket becomes constant. So we can write this one as V is equal to Q by 2 pi epsilon 0 into some constant K, into some constant K. Okay, so now this has no meaning actually. The derived expression till now, this term Q by 2 pi epsilon 0, this has no meaning. So we shall substitute this from this expression. Okay, Q by 2 pi epsilon 0. So what is Q by 2 pi epsilon 0? So from there we can write, so therefore V is equal to now what is Q by 2 pi epsilon 0 from this expression? So it will be Ex, right? Then we will have epsilon r. So since it is having 3 medium, so I am writing here, I am using epsilon rx, not r3, sorry, I am using epsilon rx, right? Epsilon rx. Then we will have, definitely we will have x, and then finally we will have this k. So from there we shall have Ex, it should be equal to V by K, which is constant. It will not create any impact. Then we shall have epsilon rx, and lastly we have x. So this expression is extremely important to understand. This expression is extremely important to understand. So as we can see, electric stress is a function of two variables. There are two variables in this case. Okay. There are two variables in this case. Now I just recapping little bit. So if we have a model like this, where we have a central core, where, let me erase all parts, where we have a central core, like this, and surrounding to that core we have a n number of dielectric medium. So that model is called capacitance graded model, and we are interested to find out what will be the electric stress variation from this conductor surface to the outermost surface. Okay, so from we want to measure Ex as a function of course x. However, we have seen if we traverse in this zone, so we encounter three different dielectric medium. First epsilon r1, second epsilon r2, and lastly epsilon r3. So Ex is not only the function of x only, that means distance only, but also Ex is found to be the function of epsilon r will also. Okay. So that we shortly see how the variation of Ex will vary as we move from conductor surface to the outermost surface. So let us see. So let us have a look. Yeah. So this is my y-axis. This is my x-axis. Okay, we have different levels, right? At this point, we have x equal to r. At this point, let us say we have x equal to r1. Let us say at this point we have x equal to r2, and let us say at this point last we have x equal to r3. Now at conductor surface, what will be E? Let us write down what will be E. So it will be V constant, K constant. Now epsilon Rx becomes epsilon R1 and X becomes smaller. This is the expression. So this is the expression of E conductor. So this much electric stress occur on the conductor surface, E conductor, which is given by this formula. Now why should I have written epsilon R1? Why should I have written epsilon R1? You see, the reason being, we are measuring the electric stress on the conductor surface itself, right, at this point. Okay, at this point. So you see, at this point means we are under the influence of medium 1, dielectric medium 1. We are that means you see this voltage difference is V1. Now V1 is what? It is that if you take one charge from R1 to R, if you take one charge from R1 to R, then you need to invest some energy. That energy is the potential difference. So as you move from R1 to R, you encounter epsilon R1. Okay. So as you encounter epsilon R1, so as long as you are sitting on the conductor surface, as long as, please understand, as long as you are sitting on the conductor surface, you are under the influence of medium 1, and hence your epsilon Rx becomes constant. So this will be the my conductor surface. Now as you now if you go outside, so if you go outside, so if you go in this way from R to R1, so as you can know, your electric stress varies by rectangular hyperbolic nature, right? So in this way, electric stress started to dropping down little bit, and at some point of time when it reaches at conductor dielectric interface 1, that means at this point, let us say this is point number 1. Now at this point, a sudden jump you will observe. A sudden jump is observable either in this direction, either in this direction or in this direction. Both are possible. Either in this direction or in this direction, both are possible. Why? How both are possible? Now why this, first of all, why this jump is observable? Why this jump? The reason being, so there are two questions at this point. So as I told you, the moment you are on the dielectric interface 1, that means this point, that means the point number 1. So you observe a sudden jump like this, either in this direction or in this direction. So first of all, the two question comes, why this jump and which direction the jump should occur. So these two questions I try to answer. Now why this jump occur? To answer this, you see, the moment you come at this point, the moment you come at this point, that means the conductor 1, sorry, not conductor 1, point number 1, that means it is the dielectric interface between dielectric 1 and dielectric 2. So the moment you are coming at this point, the point number 1, you are no longer under influence of dielectric medium 1. Okay, you are, I repeat, the moment you are sitting on this point number 1, you are no longer under the influence of the dielectric medium 1. Now you are influenced under the dielectric medium 2. So the reason, the moment you come at this point, point number 1, so it experiences a certain medium change. So certain medium change. So at this point, your epsilon R1 becomes epsilon R2, because you are at now this point, so you are under now, so this medium, let me sketch properly. So this is the medium of filled with epsilon R1, right? So this is the medium filled with epsilon R1. Now this portion is filled with epsilon R2. So from R1 to R2, right? From R1 to R2, this medium has been filled with epsilon R2. Now the point of argument is that the moment you are at this point, your influence of epsilon R1 has gone. Now you have come under the influence of epsilon R2. So at this point, epsilon R1 becomes epsilon R2. So this is the reason a sudden jump it is observable. Sudden jump either in this direction or in this direction. So this is the answer of the first question. Why this jump? And now coming to the next question. In which direction you should observe this jump? Now the answer is, now you see the epsilon R1 may be less than epsilon R2. Epsilon R1 may be greater than epsilon R2. It depends. Okay. It cannot be equal, because if it is equal, then the mediums are same. So now see, I try to understand what will be the different consequences if these two comes. Now, since epsilon R1 becomes less than, so the moment at this point epsilon R1 becomes epsilon R2. So you see, E is given by certain expression. Now for the time being, I am writing it is V by something, it is proportional to epsilon Rx. So since the epsilon R1 becomes 2, so 1 becomes 2. So initially it was 1, now it has become 2. Since epsilon R1 is less, so your denominator increases. So since your denominator increases, your numerator, the result will fall. So your magnitude will fall. So at this point, since epsilon R1 becomes less than epsilon R2, then you will, due to this certain change of medium, you will experience a fall in dielectric stress. So you will experience a droop like this. So this is the case when epsilon R1 becomes epsilon R2. Now think the reverse thing, the opposite thing. Now since the second case, when epsilon R1 becomes greater than epsilon R2, so as 1 becomes 2, so you see the denominator falls, denominator decreases, because epsilon R2 now reduces from epsilon, it is smaller than epsilon R1. So the denominator reduces. As the denominator reduces, the result will go up. So this is the case when this you will experience a sharp rise when this epsilon R1 greater than epsilon R2. So I am writing again afresh with a different color. So you see, when or rather you will surely experience a dip. It can happen, it may happen in this direction when epsilon R1 greater than epsilon R2. However, epsilon R becomes also, it may go high like this. It happens when epsilon R1 becomes greater than epsilon R2. Okay, so both can be happened, right? So it can, after reaching electric variation of electric stress, after reaching at this point, it can go in any direction depending on the value of epsilon R1 and epsilon R2. At this point, I must make a mention here that you consider this case. This is very important. Epsilon R1 greater than epsilon R2. So if the epsilon R2 value is so small than epsilon R1, so if it is so small, it may happen that epsilon Ex will rise surely, but it can rise to any level, so it can go beyond the maximum stress on the conductor surface. It can go beyond this value. It is possible, right? At least theoretically it is possible. So till now what we have learned for single core cable case, that is the maximum stress occurs on the conductor surface. Maximum stress occur on the conductor surface. That is necessarily not true for all practical cases. The maximum stress can occur in some dielectric interfaces as well, like explained in this case. Okay, it totally depends on the value of epsilon R1 and epsilon R2, how much value you have chosen for different dielectric mediums. Now after settling down at this point, so I am repeating again, the jump is due to the sudden change of dielectric medium, and in which direction it is totally dependent on the epsilon R1 greater than epsilon R2 or less than epsilon R2. Okay, both can happen. Both can happen. Okay, so it can either go in this way or it can go in this way. So after whatever direction it can go, after settling down again it starts if you analyze the next medium from R1 to R2, so again it is following the same criteria, the rectangular hyperbolic. Now after reaching at this point, that means the dielectric interface 2, again it will experience a jump either in this direction or in this direction, depending on the value of epsilon R2 and epsilon R3. What is their relation? Whether they are greater or whether they are smaller. Okay. So in this way, roughly we shall get a sketch like this. So this is conductor surface. So we may have a spike, then again we are drooping down, then again we may have a spike, then we again are drooping down. In this way, we have a roughly sketch like this. Now, theoretically, it is nice explained that if that epsilon R1 into R1, this product epsilon R1 into R1, epsilon R2 into R2, and epsilon R3 into R3. These products you can make equal, at least theoretically. Then it is nicely observable that electric stress on each conductor or each dielectric interfaces are equal. So whatever stress you will get on the conductor surface, that much you will occur, that much stress you will observe at this point, the same you will observe at this point. Okay. So this is the you see, this is for theoretical calculations. Practically, as I told you already, practically it is very hard to achieve. Practically it is very hard to achieve. And now at this point I'll briefly demonstrate a problem on this. Okay. So let us come to the problem. You see, this is the conductor. This is the conductor, right? It is supplied at 25 kV RMS. Now let me read out the statement of the conductor. A conductor having 3.5 centimeter in diameter passes centrally through the porcelain bushing, having internal and external diameter of 4 centimeter and 10 centimeter respectively. So this is the porcelain bushing for you. This green shaded region is the porcelain bushing for you. And this region, the yellow shaded region, is the transformer oil. So this is a practical example of this type of model. This is a practical example. So so conductor 3.5 centimeter in diameter. So R of the conductor is 1.75. 3.5 by 2, that will be equal to 1.75 centimeter. Now diameter passes centrally through a porcelain bushing having internal and external diameter of 4 centimeter and 10 centimeter. So 4 centimeter means this much. Okay, as it is given. So that means if you draw an analogy with this diagram, so your conductor is this, so here it has to be 1.75 radius. Now that means this region, is transformer oil, filled with transformer oil. That is, and the yellow region is the porcelain bushing for you. So that porcelain bushing have some internal diameter, that means it is R1 double and R2 double. Okay, so R1 double, that means if you draw, so R1 has to be 4 by 2, that means 2 centimeter, and R2 here 10 by 2, that means 5 centimeter. Now the next part, the potential difference between the conductor and earth surrounding is 25 kV. So it is given at, conductor is given at 25 kV RMS voltage. Now determine the stress on the conductor surface. You need to evaluate E conductor. There are two conditions: when air is there in between porcelain and when transformer oil is there. So this portion, yellow portion, we have two options: either we have air or we have transformer oil. So this is the problem. Now I must mention here that epsilon R1 it could be, so your first dielectric medium is either oil or transformer, or either transformer oil or air. So in that case, epsilon R1 for air, it should be 1, its standard value, and epsilon R1 if it is a transformer oil, then it should be 2.1. I think it should be, yeah, 2.1. Now medium 2 is the porcelain. Okay, medium 2. So epsilon R2 as it is given, that is for porcelain, it is I think it is 5. So you know the relation E is equal to, from this expression you can evaluate V by K into epsilon Rx into X. That is the fundamental formula you have with you. Now let me first evaluate what is K. Now what is K? K is given by this formula. You see this formula. So you will require only these two parts, this part and this part. So K is, I am writing, K is 1 by epsilon R1 if we have air into ln R1 by R, then we have 1 by epsilon R2 which is for porcelain into ln R2 by R1. So let me put it down, the values. So AR is 1 by 1, so ln, so now what is R1? R1 is 2 and R is 1.75. For porcelain it is 1 by 5 ln. What is R2? R2 is 5 by R1, that is 2. So if you solve this, you will get this K value as 0.316. So now you are ready. What will be E? E conductor. So you have 25 kV RMS. You have K is equal to 0.316. Now what is epsilon Rx? Now you are measuring the electric stress on the conductor surface. So you are under the influence of dielectric medium 1. So you should use epsilon R1. Epsilon R1, it is 1 in this case. And you should X. What is X? Conductor surface means X is R. So it will be 1.75. So if you solve this, you will get 45.2 kV RMS per centimeter. This is the conductor. This is the stress on the conductor when air is there. Okay, in between conductor and porcelain. Now coming to the second part, when transformer oil is replaced or air is replaced by transformer oil. So the second part, so we will have K, that means 1 by epsilon R1 for oil into ln R1 by R plus 1 by epsilon R2 into ln R2 by R1. So now starting putting the values. Now epsilon R1 for oil, as it is given, it is 2.1. It is 2.1, so it will be 1 by 2.1 into ln 2 by 1.75 plus 1 by 5 ln 5 by 2. So now if you solve this, you will get this value as 0.246. So now for the second case, you start solving what will be the electric stress on the conductor. Again putting the same values, your V is 25 kV RMS divided by, now what will be K? K is 0.246. That is multiplied by, now epsilon R1, now the air is substituted by transformer oil, so it will be 2.1 and the radius becomes same, it is 1.75. So as you solve this, you will get a value of 27.65 kV RMS per centimeter. So we have seen two cases. So when we have air, then we have seen the conductor stress on the conductor is 45.2 kV RMS per centimeter. And when we have transformer oil as the dielectric in between the conductor and porcelain, we have the stress on the conductor 27.65 kilovolt RMS per centimeter. Now if you draw an analogy between these two or compare these two, you should not expect this to happen in your system. It is strongly not recommended. Because if you use air, then it is having a high value, very high value of electric stress. You know, if we have a 1 centimeter gap, and then within that gap, if a stress of 30 kV peak comes or voltage comes, then that gap will be flashover. Okay. So 30 kV peak means it is roughly 21.2 kV RMS. So almost it is the more than double voltage it is coming on the conductor surface for the same 1 centimeter gap. So it is very, very dangerous value if you play with air or if you have the air as your dielectric medium. On the other hand, if you have the transformer oil, you see the conductor stress it's very low, 27.6. At least this is the safe value. So it is having a very low value as compared to this. So transformer oil is always better, is a better alternative than air in case of a transformer. Okay. So that is then another example. Okay. This is the example through which it is demonstrated a practical example of capacitance graded system. That is this is the conductor. Let us say this is the centrally passing, and we have the porcelain bushing. Like this. Sorry. This is the central conductor. We have the porcelain bushing like this hand, and in between either we have transformer oil or we have air as per this problem, but mostly we have transformer oil. So this is the practical example of capacitance graded system where the central conductor is surrounded by 2 or 3 dielectric mediums, and most importantly in this case we have found that whatever you have learned, that maximum stress that it will occur on the conductor surface, it is necessarily not true always. It can also occur on the some dielectric interface as well. It's depending on the value of epsilon R1, R2, R3, whatever. So I am stopping here. So in the next class, we shall discuss some more topics on this underground cable. Thank you.